Oops. Mhm. Okay, I know I know we've talked about this topic before, but we're going to go through it pretty quick. Chapter 3, Section 2. Yes. Measures of variation. What does measure of variation mean? What? Bless you. Not really that. That's what I mean by variation. What this looks at is the last thing we talked about was measure of central tendency. What is a measure of central tendency? Mean, median, mode. Everything that has to do with the center of the data. Because the mean is what? It means the average. Median is the what? The actual middle one. And the mode is most frequent. That's not really a central tendency. But what if we have two data sets? We have two data sets, and their averages were equal. Remember we talked about this about the paint cans, paint samples. How would you determine, are they truly equal? Are you missing something? Oh, it's section 1 and 2. Oh, let me see. Here's section 1 and 2. Does everybody have section 1 and 2? Carla? Yeah. No, that's there were two separate sheets. Yes. Oh, I have to find those. I have to find you an extra one then. Actually, I could have sworn I gave out everybody the sheets last week. If you picked up a packet last week, you have those. But so measures of central tendencies, we have the same mean. What happens if we have the same mean? So what we're going to look at now is how is that going to affect our decision on which one's better? So a variance discusses how far from the mean are the data values. Because if we looked at our data set, and if we had an average of that, and our data points look like this, if this is our average, then if that's the average, that means how far each of these individual points are from that average have to equal. Because remember, it's the average. So that means all of these numbers are equidistant on the average of it from the mean line. So some values are above there, so those are positive. Some values are below there, so those are negative. What happens when we add them up? well, they become zero. Because if it's truly the average, that means that the ones that are above it and the ones that are below it have to be equal. So the positives and the negative, they cancel out. So let's look at this example. We had our data set is this 25, 30, 35, 35, 40, 45. So what's the average of this data set? You could take out your calculators and phone a friend. Average 35. So how do we find that? The formula for the mean was add up all your data and divide by how many you have. So if we add up all of our data, what do we get? So it's 210 divided by 6, which is how many data points we have. That equals 35. So now, and that's the same thing with the other sample size. What we have to figure out now is this. To find the standard variance. Standard means that it's uniform throughout the entire data set. We're looking at how each of these vary from the mean to the individual points. The formula for this is the first thing we have to do, since we have the values of our data set. Here's x1, here's x2, and here we have our mean. What we have to do first is we have to subtract from each of our data set, we have to subtract the mean from it. Why? What's that going to do? That's going to tell us how far away from the line it is. So here we have to do x minus x bar. Remember, the x bar is 35. So 25 minus 35 is what? Yes, negative 10. 30 minus 35. Negative 5. 35 minus 35. 35 minus 35 is 0. 40 minus 35. And 45 minus 35. If we add up all these are all our distances. If we add all these up, what do we get? Yes, we get 0. We should get 0. Why? Right, because if 35 is truly our average, That means the ones that are above it and the ones that are below it have to all be equal. They have to be the same both above and below. So how do we fix that? No. What we have to do here is we have to get rid of the negatives. How do we get rid of the negatives? Square each of the values. So our formula is we have to now square each of the values. So negative 10 squared is 100. Negative 5 squared is 25. 0 squared is 0. 0. 5 squared is 25. 10 squared is 100. Now, if we add up all those, $250. So far, so easy. But that still doesn't tell us anything about our data set. Why? Because this is a very large number. It's bigger than all of our data set together. So what do we have to do next? Divide by n. We're going to look at the average of these distances. Remember, each of these are distances, how far the number is from the mean. So let's divide by n. So we have 250 divided by 6 equals 41.7. What's that? 41. Yes. So we added up all of our distances. That is our variance. What we have here is our standard variance. What that tells us is the distance up and down on all of these things averages out to be 41.67. The problem is what? The problem is when we squared it. When you square a number, what happens to it? It becomes super large. So what we have to do now is, what's the antidote to squaring something? Square root it. So we have to get rid of the square root, the square, by square rooting it. That is what's called the standard deviation. So the square root, in our case, the square root of 41.67 is what? It's just a little bit above 6. 6.7, 6.5. What is it? The square root of 41.67. 6.45. Thank you. Now, that is how far, on the average, how far each of our data points are away from the mean. That's what that tells us. The standard deviation tells us on average how far each of our data set is from the mean. Why is that important? But why is that important though? Yes, it does do that, but why is that important? Oh, I see what you're trying to say, but no, the average is average. You can't mess with the average. It's just add up the numbers and you have it. What it does tell us is how far. So the bigger the variance, bigger the deviation means what? From the average, yes. So more dispersed, more spread out the data is. So the smaller the deviation, the more compact it is. So that's what it tells us. It has to do with the median, right? With the mean, but we want a small deviation. The smaller, the better. So this is how we would in this paint sample thing. This is how we would compare the two. Even though they both have the same average, we would look at each of our data, see how far it is from the average, and determine that from there. You want to compare it to the other data? Okay, let's compare the other data. So the other data, this is for paint plant sample B. It is 10, 20, 30, 40, 50, 60. Again, we have the same number of samples. So find me the deviation. So this is what I like about this. For me, just ask for the S, for the deviation. What do you have to find? You have to find the mean. You have to do the x minus the mean. You have to do the x minus mean squared. You have to do the divided by n, and then you have to square root. So that's just one little small letter, but it means all of this other stuff. Good morning. Great yourself. Did you exercise?
No, my brother did so. He actually got your state. So after they do their, okay, we went to the boot camp back, we did boot camp, they go back to like social media. Yeah, on Friday. I wanted to ask, is they gonna let him come home? Because he told us that he flies in straight to the schoolhouse on Friday.
All depends what his MOS is and what he has to report for. Usually they give you a couple of days transition leave, but if they need him now, they'll take him right now. So
When the schoolhouse, even though things have changed, you think back in the day, the schoolhouses were closed on. Or you
good point.
Yeah, that's what I'm saying.
That's a good point. That's a good point. I don't know that I can answer that. Then it's
Okay.
I wish I could. Normally, logically, you'd say yes, but no. Sorry. Okay, we also know that the average is the same, so it's 35. Okay, so what's 10 minus 35? What's 20 minus 35? 30 minus 35. 40 minus 35. 50, 50 minus 35. 60 minus 35. So when we add this, what should it equal? Yes, if it doesn't equal 0, you did something wrong. It has to, because that way you know if it's the actual mean, it's middle between the data points. When we square them, what's 225 squared? 115 squared. 5 squared, I could do that one. And the other ones are going to be the same. 225, 625. Then what? We have to add them up first. Because now we have to do the summation of x minus x bar squared, which is what? What's that? 1,750. So now we have 1,750 divided by 6, which is what? So that's s squared. That's s, I'm sorry. So now we square root it. So what that one says, what that one's telling us, compared to the other one, what was the other one? This is B. The first one we had was 6.45. So which paint sample is better? Right, because that way we can start budgeting. We can say when the next time we have to paint our houses, when we have to start buying paint. So that's what it's used for, is you want to be able to compare and see how it varies, see the dispersion. Because the smaller the dispersion, the more accurate the numbers, the more accurate the samples are. So we have a problem here. Does this formula what if we had intervals? Oops. Oop. 5, 10, 15, 20.5. What if we had intervals? Why? That you're right, it's a midpoint, but wrong answer. Why would we need the midpoint? Well, first off, let me give you the frequencies. 1, 2, 3, 5, 4, 3, 2. What's the modal class? Right. This one's the modal class. Where's the median? How do we find the median? No, not the median. The median is the middle number, the physical middle number. Remember how to do that for intervals or grouped data? Add up all your frequencies. So we get 5, 10, 15. There are 20 pieces of data. What do we do with that? Once you have the sum of all the frequencies, then what do? We're trying to find the middle number. Divided by 2. Because I want to find the middle number, so I fold it in half.
So is
No. No, the middle number is not, it's not 10. It's the 10th location. Remember the process. If you take the frequencies divided by 2 and it's an integer, this is the location. We have to go to the next number also. So what is the 10th number? What's the 11th number? How do you know? Well, in order to find these, what do we have to do?
that's
You have to find the cumulative frequency. Remember what the cumulative frequency was? It's a running total. So the first set has 1. Then we add 2 more, we now have 3. Now we add 3 more, we have 6. Now we add 5 more, we have 11. Add 4 more, we now have 15, then 18, and then 20. So where are the 10th and the 11th numbers? Right, because the 10th one is here somewhere, and the 11th one is also in this one. So this is your medial class. Because when we deal with group data, it does change.
I'm still low. I know how you got it.
Take the frequencies, add them all up, divided by 2, because it has to be in the middle. The median has to be in the middle.
Okay.
So it's 10. That's the location of where the middle number is. And if it's an integer, you have to go to that location and then go to the next one, add the next one also. Here's what's happening. If I only had 4 pieces of data, what's the median of that group? What's the middle number? How'd you get 5.5? Well, you have to use a formula. You have to use a procedure in mathematics. It has to be uniform in every example. Just because it's a small data set, don't take any shortcuts. How did you find it? Well, we had how many pieces of data? Divided by 2, that equals 2. So I go to the second data point, is 5. I add the next one to it, and then I divide by 2. So 11 divided by 2 is 5.5. That is how we find your median. Because it's a process, and it works now. Since you have the process, it works no matter how big it is. Has to be, yes, very true. Whenever you have a data set, always put it in increasing order.
So this was here for the CFs, you just added those and that's how.
The CFs, cumulative, it's a running total. So in the first one, so what this says, in this first line down, how many pieces of data are there? There's only 1. Now with this one, I have this one and 2 more, so now I have 3. Now I have 1 plus 2 plus 3, I have 6 total. Right, so it's whatever you have here, add the next one there. Take that one, add that one, we get that one. That's how you find the cumulative frequency. Didn't we go through that before? Yeah, we did. Look at your notes. Cumulative frequencies, we did it about 2 weeks ago, a week and a half ago. Cumulative frequencies. Same way. What's that? Yeah. Because that's the only way I can explain it. I did the same way. No, I did the same way. It's just that there may something that may have been in your head. But I've been teaching the same way for 24 years. So yeah, there's only one way to do cumulative frequency. It's a running total. So everything from that point down, what we have. All right, so now, how do we find the variance and deviation of grouped data? Remember, our formula is that. Actually, the first time we introduced this formula, in general, we use an n-1 for samples. The n-1 removes any possible error you had in data collection. So this is the true formula we have for, so if you ever use a calculator or Excel or some other packaged program, always test those values compared to what you calculated by hand. Because it may have n-1 as a denominator, or it may have n as a denominator. It won't tell you, it'll just spit out an answer. So that's why you always use your own test data, a small set of data, calculate it and see what the computer has. So we can find the mean. How can we find the mean? Do what with frequency? No, we did the cumulative frequency so we can find the median. So we know exactly where the set is. I know I've thrown a lot of stuff in there. But for us to be able to find the mean, the variance, the deviation, or pretty much anything else, you can't use intervals. You have to find a number that represents that interval. That's where the midpoint comes in. So the point that represents this interval is what? So what's the midpoint of this interval? How do you find midpoint? Add the two numbers and divide by 2. So we're looking at the average of those two numbers. So it's 15, 16 divided by 2 is 8. So we found that by 5.5 plus 10.5 divided by 2. How far is it from one set to the next set? 5. Yeah, because 10 minus 10.5 minus 5.5 is 5. So that means from our midpoint from the first set to the next midpoint, you add 5. That'll be 13. Then 18. Then 23. Then 28. Then 33. And 38. Why do we need to have the midpoint? Because that's going to represent that interval for us. We need, in order to find the deviation and variance, we need to know the average. How do you find the average of a frequency, a grouped set? Remember, it used to be add up all your data and divide by n. But now we have frequencies. So what we have to do now, each data element times its frequency, add up all those and divide by n. Why is that? Because if, let's say we had 4 3s and we're gonna add them together. The basic rule of multiplication says, since we have 4 of the same numbers, we could just multiply 4 times 3. And that's what this is all about. So instead of adding up all these x's that are the same x, we multiply how many there are. But since our x's are intervals, what do we use instead? Yes. Then we use the midpoint. So our mean is going to be, take the midpoint times the frequency and divide by n. That's how we find the mean. So back in our set here, we have to multiply the midpoint times the frequency. So this number times this number. 1 times 8 is 8. 2 times 13 is 26. 3 times 18 is 54. Three times 18 can't be. We're doing f times x of m. Then we have 5 times 23. 4 times 28. 3 times 33. And 2 times 38. According to our formula, then we add them all up.
Okay.
Yeah. So add up all those, what do we get? $490? Okay, so we have 490 divided by our n is the summation of all the frequencies. So divide that by 20. The zeros cancel, so we have 49 divided by 2.
Are we gonna?
No, leave it as decimal. Because the average, does the average have to be one of the data points?
Oh, yeah.
Or no, I'm asking is our average, since our data points are integers, does the mean have to be an integer? No, by definition, because if we had 2 of them, 3 and 4, we're going to have a fraction, a decimal. So leave it as a decimal. So our x bar is 24.5. So now we have our formula we can use for the deviation. We have the summation of the midpoint minus x bar squared over n times 1, n minus 1. So that's our formula. We have x sub m. X sub m is right there, is this column. We have x bar, that's what we just found here. N is 20. What do we have to do now? Nope. What do we square? Do we have x sub m minus x bar? We don't even have that yet. We have to create that. We have to go x sub m minus x bar. We have to build our table from what we have. So x sub m minus x bar. Remember, x bar was 24.5. So 8 minus 24.5. 13 minus 24.5. 18 minus 24.5. 23 minus 24.5. 28 minus 24.5. 33 minus 24.5. 38 minus 24.5. No, 38 minus 24.5.
Okay.
Okay, there's going to be a little problem here because if we add those up, what do you get? Add them up. Don't take a guess. This is a math class. Never guess. Why is that the problem? It's not zero. And why is it not zero? Because we use the midpoint. Assuming all our calculations are correct, find our midpoints, time our frequency. We do those correctly. And we add those correctly. But because we have an interval and we only took 1 point of that entire interval. That's where the problem is. But we have to keep on going with what we have. Remember, these are all approximations. So now what do we do with this column? We have to square it. Because remember, the formula is xm minus x bar squared, then you add up all those. So now we take each of these values, add them up, or square them and then add them up. Now you see why using Excel or something like that is much easier. So what did you get for the final answer? For,
Negative.
can't be negative, because when we square it, it gets rid of all the negatives. I don't know. Once you said negative, something went wrong with your calculation, so we can't use those. Well, yeah, since, okay, when you square all those, what do you get when you add them all up? All right, so that's the, so that's the top part. And we have 20 minus 1. So what is 716.25 divided by 19?
Mm.
6.13. That's the final answer? So that's why you have to be very careful when we do these numbers. If any of these numbers were entered incorrectly, and any of them wrong, you get, look at this. This is 6.13. This is on the average of how far the numbers are from the mean. But the numbers themselves vary. I mean, it goes from 5.5 to 40.5. So that's a pretty small deviation. On the average, it means that that's how far they are from the mean. So what's the difference between a variance and deviation, formula-wise? The what? Yep, that's it. So S squared is what? But in names, the name. Yes. This is the standard variance. And when you square root it, it becomes the standard deviation. Now, very painful formula. Very painful. Why? Because we have to do the X bar, X minus X bar. It's too much. Here's a shortcut. And the deviation is just square root of it. Why is this one a lot easier to work with? Don't ever use PEMDAS. If you want to fail the course, say that word again. It's like Beetlejuice. PEMDAS will make you fail math so fast. No. The reason this is easier, because what all do you have to do here? You don't have to find the mean. You don't have to subtract it from the median, the midpoint from the mean, and you have to square them. This is a lot easier. So if you have ungrouped data, or if you have an X value and a frequency, not even a frequency, it doesn't matter the frequency. Here you just take the X values, square them, and then add them up, as opposed to add up all the X's, then square them. How are these two different? So how does that change? Is it gonna change the answer?
Oh, first, this second one, that the sum of the x values and then square.
Will that change the answer though? Because if I just add up all my x's and then square them, or square them, then add them, is it gonna be the same thing? Let's look at this. 2, 3, 5, and 6, and 9. Let's see if both of these, if they're the same. So on the left side, what is it telling us to do? Square all the x's. So 2 squared is 4, 3 squared is 9, 5 squared is 25, 6 squared is 36, 9 squared is 81. Then add them all up. The other one says let's add them all up first and then square it. So it's 25. So 25 squared is, are they equal? No. So yes, it has to do with the order of operations. You have to be very careful about that. This one says you square x first and then add it. This one says I add up all my x's and then square it. Let's use the same data set. 20, 30, 40, 50, and 60. Find S using the shortcut. Yes. The formula? Actually, I should just wrote it down again, shouldn't I have? Okay. What's our N? Yes. X. We only have 6 pieces of data. What's that? What number am I missing? 20, 30, 40, 50, 60. Oh, 10. So to read this formula, what number goes inside there? What number goes inside the parentheses?
Mhm.
210. So that's 210 squared. This n in front of here is 6. Now, what number goes inside this parenthesis? Well, we have to square the numbers first and then add them up. $100, 2,500, 3,600, 100. 41, 77, 78, 87. You guys should be using calculators and stuff. Is it 9,100? I guarantee you, just watching me do it's not going to help you. You should be doing it yourself. So when you leave this room, you can do it yourself as homework. What goes on the bottom? Which is? Yes. Actually, this is the variance. This is the equation for the variance. How do I know it's the equation for variance? Yeah, well, it doesn't have a square root. Since there's no square root over here, it should be s squared. So, and if the square is gone, then there has to be a square root on the other side. Okay, so what's the final answer here on this side? Well, let's do it piece by piece then. Six times 9,100 is 54,600. 210 squared. We have 10500 over 30. Was it? Well, that's easy. 350? That's not, it wasn't too far off. So that's the variance. What do we do now? How do we find that? Square root it. So the deviation is the square root of 350, which is just short of, what's that? We're using one decimal. Okay, if you want to put 870.1, you can. All right, so this is with ungrouped data. How do we change it using the shortcut method? This is when we have just regular x's. What if we have intervals? How do we change this equation for, this is for ungrouped. How do we change it for group data? So instead of X, we use the midpoint. There's one other change we have to make. What's that? Well, the end's gonna be the same. It's gonna be the summation of all the frequencies. Whenever you have group data, you have frequencies. Not really cumulative frequency, because think of this one. When we add up, if we add up all the X's, we just add up all the X's. But what if we had, right, who said that? Yes. You have to multiply by its frequency. Because if we had one here and it happens 5 times, we have to use this column. So whenever you have group data. So now, so in each one of these, it's going to be the midpoint squared times the frequency minus summation X times the midpoint times the frequency, all of that squared.
That's time to.
Yes. So this is the important part. You have to understand now, when you give you the formula, that's the easy part. Can you create the table for it? Let's use the same data we just had a second ago. We use a shortcut method. This is my X, my data class. So and the frequency. So it's 1, 2, 3, 5, 4, 3, 2. Because once you learn how to create these tables, it's just plug and play. So in order to use this, we have this information. What do we have to find first? There's no cumulative frequency there. Do we have F right there? Do we have X sub M? What is X sub M? The midpoint. So we have to find the midpoints. And we found there's 8, 13, 18, 23, 28, 33, 38. So what's the next column we have to create here? Let me see. Okay, that's for that one. What about this one? Right. We have to find the midpoint squared. So we have to square all the midpoints. So 8 squared is what? 64. 13 squared. 18 squared. 324. 23 squared. What is it? 529. 28 squared. 33 squared. And 38 squared. Okay, we have all the pieces. It's like when you're in the kitchen cooking, you have to get all your ingredients first, your mise en place. Now we can start combining them. So for this first one, we have to add what? X squared times F. So we multiply X squared times F. 1 times 64 is 64. 2 times 169 is 338. 3 times 24, 972. 5 times 529, 4 times 784. 3 times 389. Can't be. 3 times 1,000 is 3,000. 3267 and 2888. So we add up all these. That goes in the first parenthesis. So what I'm trying to do is, do you see how we build these charts? You see what the formula is, what we need, and we create the headings for each one of those as we're building. So that takes care of this parenthesis. What about this parenthesis? What do we need there? Yeah, so do we have X sub M times F anywhere? No, we don't. Oh, this should be a midpoint. So we need an X sub M times F. This one's X squared times F. So now we just need that. So it's these two, 1 times 8, 2 times 13, 3 times 18, 5 times 23, 4 times 20, 4 times 28, 3 times 33, and 2 times 38. Then we add up all those. This one, what is it? 498. How about the other one? Now you have everything you need just to plug and play. So N was what? No. N is the summation of all your frequencies. There's 20. So it's 20 times x squared times f, which is this one, which is 13,310 minus 490, 20 times 19. So this way is a lot easier. I mean, there's still a lot of number punching, but it's a lot easier creating these columns. Nope, it's 490 squared. So what's the final answer? 0.68. So typically it's one extra decimal point than what you started off with. So 68.7 is our standard variance. So what's our standard deviation? Oops. Very good. So now we've looked at small data sets, large data sets with frequencies, group data, and ungrouped data. So I put in this list for y'all. Uses of variance and deviation. To determine the spread of the data, the variance and standard deviations of large data, to see how they're dispersed. To determine the consistency of a variable, to determine the number of data values that fall within a specified interval, and is used a lot in inferential statistics, where you make inferences about things. That's pretty much what that's what I try to do. Yeah, it makes it much easier to go through it this way.
How about
Yes, sir.
like play bigger? You stand over on the software.
They both should give you the same value. How far is it off?
When you take the same data, like you just standard, it will be like 6.13. The standard deviation. I don't know, we get 8.4.
For a deviation? Well, remember, and the other one, we had the 6.7. We also had a negative summation of the x squared. So that one, I have to go through, check all the numbers again for that one, because we're not supposed to have a negative to begin with. So that's it. This one's a lot easier to work with. And so it's a very good question. I'm glad you asked. I will check that out in the next class. Which one is more accurate? But they should both be very similar, very close in the answers. But you're right, that's a huge difference from 8.3 to 6.7. That's a big difference. All right, now, so far, this is when we're looking at the same thing. This one was examples of paint. Yes. Oh, I'm sorry. I'm so sorry about that. Okay,